A lot of times metals can react with acids or ionic salts, and these reactions are occasionally called displacement reactions because they take the following pattern. This would be an example of something you might recognize as a single displacement. The reactant A replaces the B in the BX compound. An example using real elements is the reaction of iron metal with nickel nitrate. This is actually an example of a fairly simple redox reaction. This version is a molecular equation example, but in a previous video I showed the net ionic equation version, which I'll reproduce now. Once it's shown in terms of an ionic equation, it becomes much easier to see that the iron loses electrons to become iron 2+, so it's oxidized, and the nickel 2+ ion gains 2 electrons in order to become nickel solid, so the nickel 2+ is reduced. And this is why oftentimes, if you're given an equation and you're not sure if it's redox or not, it's a good idea to break it down into the net ionic form, because it makes it a little bit easier to see what's actually happening in the reaction. So the activity series is a chart that was experimentally developed, and it allows you to predict the ease of reactivity. So things closer to the top of the table are easier to oxidize, and things closer to the bottom of the table are much harder to oxidize. And to use the table is actually quite easy. Any metal that's on the table will react with any ion below it, and it will not react in any other way. And that's it. Any metal will be oxidized by any ion that is lower on the table. The metal won't be oxidized by any metals that are lower on the table. It won't be oxidized by any metals higher on the table or any ions higher on the table. Only one combination will work. And we'll run a couple of examples, and we'll start with something in the middle of the table, and we'll look at cobalt. So cobalt is a metal. Cobalt solid can react with any ion that is below it on the table. So cobalt will be oxidized by nickel ions, tin ions, lead ions, hydrogen ions, etc., all the way down the table. But it will not react with any metals below it, any metals above it, or any ions above it. So we'll look at every possible combination of reaction types. In the first one, we'll look at cobalt reacting with a metal above it on the table. This leads to no reaction. Barium is above cobalt solid on the table. Remember that this is supposed to be a redox reaction. So the thing at the top is easier to oxidize, so the barium solid has to oxidize. And if that happens, barium goes to barium 2+ and 2 electrons. So barium is oxidized, no problem there. The problem arises when you remember that redox reactions happen in pairs, a reduction and an oxidation. The barium oxidizing is the oxidation part, but the reduction part involves the gain of electrons. If barium is oxidized, that means the cobalt has to be the reduction. And that means that we would produce cobalt 2-, which is absolutely outrageous. That can't happen. Remember, cobalt is a metal, and metals traditionally don't gain electrons to become anions. This is absolutely not going to happen. In the second combination, we'll look at cobalt reacting with a metal below it. So we'll look at cobalt reacting with lead. And this reaction also does not happen. So again, the higher of the two elements must oxidize, because higher on the activity series implies easier to oxidize. So cobalt can lose 2 electrons, absolutely. The cobalt oxidation can happen no problem. The issue becomes lead solid has to be reduced then, which means you'll make lead 2- ions. And as we mentioned earlier, making a metal an anion is absolutely unlikely to happen. So this one also won't work. In the third possible combination, we'll look at cobalt reacting with an ion above it. So we'll look at cobalt and barium ions. And this also leads to no reaction. The thing that's higher on the activity series must oxidize. Barium 2+ cannot lose any more electrons. This reaction just will not happen. The barium has already been oxidized to give you a 2+ charge. It can't oxidize anymore. And on top of that, the cobalt would have to be reduced, which would again give you a CO2- charge, which is just ridiculous. In our fourth possible type of combination, we'll look at cobalt reacting with an ion below it. So we'll look at cobalt and lead 2+ ions. In this example, cobalt is higher on the activity series, so it oxidizes. And this process is absolutely possible. Cobalt is neutral. It can lose 2 electrons to form a 2+ charge. That's quite easy. And then those 2 electrons can be used in the reduction of lead 2+. And this process is also totally valid. So all 4 combinations, only one of them will give you a valid result. And in all of the examples that we just did, every reactant was either going to lose or gain 2 electrons. They were going to gain or lose the same number of electrons. But you can also have reactions where the number of electrons that get exchanged is different. In this example, we'll look at cobalt reacting with silver ions. Cobalt is higher on the activity series, so it's going to lose 2 electrons. And silver ions are singly charged, which means they only need 1 electron in order to convert the silver ion into the silver metal. And to deal with this, all you have to do is some simple chemical equation balancing. It looks like for every single cobalt atom you have that's oxidized, you can reduce 2 silver ions. So all you have to do is change the coefficients for silver ion and silver metal to 2. And while we've only looked at metals reacting with metal ions at this point, you might notice that hydrogen is in the activity series as well. Because hydrogen and the hydrogen ion are present in the activity series, metals can also interact with acids, which produce H+ ions. So we may as well do an example where cobalt reacts with HCl. Remember, most redox reactions are a little bit easier to process if you only work with a net ionic equation situation. And in this case, aqueous HCl is really consisting of H+ ions and Cl- ions. And the Cl- ions are not relevant. They're going to behave like spectators. So a simpler way of representing this is cobalt reacting with H+. And this situation is one that we've encountered before. Cobalt metal reacting with an ion that's below it on the activity series. And this is another one of those situations where the number of electrons need to be balanced.